Hello guys, welcome to another video of Shallow Foundation series. Continuing with the videos, we have been doing numerical from this chapter. Today we are going to discuss and solve numerical related to effects of water table in bearing capacity of foundation of different shaped footing. And one message for the viewers is that you are requested to comment the topic name on which you want videos to be available on this channel. So now continuing with the lecture, let's start with the example problem. We have question as a footing 2 meter by 3 meter, that is rectangle footing, is founded 1.5 meter below the ground level. Depth of foundation is 1.5. Clay having an angle of repose and C cohesion 10 kPa. What will be the allowable load which can be carried by the footing if the load is eccentrically applied with the eccentricity along x and y direction as 0.25 and 0.35 respectively. The center of footing in plan is taken as origin. The water table is located 1 meter below the ground level. Assume soil above water table is dry. Take dry and saturated unit weight of clay as 60 kN per meter cube and 20 kN meter cube, where we have the value of NC provided as 50, N cube 42 and N gamma as 46. So let's first write what has been provided. We have size of footing is provided as 2 by 3 meter. Depth of foundation is provided as 1.5 meter and C is given as 10 kPa, which is equal to 10 kilonewton per meter square. Similarly, we have NC provided as 50, NQ as 42 and N gamma as 46. We have eccentricity as given as 0.25 in x direction and those in y direction is given as 0.35 meter. Now drawing the figure of the elevation, it will look like this. This is the elevation. We have QS 1000 kilonewton per meter. We have depth of foundation is 1.5 meter and water table depth from the base is 0.5 meter. This is the water table. We have depth of foundation is from the base And similarly we have water table 1 meter below the ground surface, and above the water table, that is the dry sand, we have a unit weight of dry sand is given as 16 kilonewton per meter cube, and those below the water is given as 20 kilonewton per meter cube. Now here the load is applied eccentrically, so the length changes. Length changes occur as length changes is b minus 2 times ex, and length changes here this provides us the change in width, and this provides change in length. So we have b given as 2 minus 2 times ex is given as 0.25. sorry, let's write here in the given 0.25 meter, and ey, that is the eccentricity load in y direction, is 0.35 meter. 2 minus 2 times ex, where ex is 0.25, which gives us change in width is 1.5 meter. Similarly, this gives us change in length is which is 2.3 meter. Now we have for the rectangular footing, to calculate the ultimate bearing capacity, CNC 1 plus 0.2 b by L gamma df NQ times RW1 plus 0.5 gamma beta b in gamma 1 minus 0.2 change in width upon change in length times RW2, that is water reduction factor. Now we have all the value provided. Expect the value of RW1, that is the water reduction factor, and in this case, as we see here, water table is 1 meter below the ground, 1 meter below the ground. So gamma is in NQ term is taken as the average gamma, that is unit weight, while in this in gamma term is taken as gamma sat. So let's find RW1. One by 2 1 plus JW1 by DF1, which is 1 by 2. Here JW1 is the this distance from water table to ground surface is the JW1, which is 1 meter. 1 plus 1 by depth of foundation is 1.5 meter. Similarly, RW2 is given as 1 by 2 1 plus JW2 by DF So 1 by 2, as we have the water table above the base of the footing, so here JW2 is 0, so this becomes 0, and on simplification this gives us 0.83, and other is 0.5. Now for calculating the average unit weight, this is how we can calculate the average unit weight. As we have 16 is the initial unit weight of dry part, and the depth of that part above the water table and below the ground level is 1, that is 1, and 2 is the saturated unit weight as given in the problem, and 0.5 meter is the difference of depth between the water table and the base of footing, and that is d1 plus d2, which gives us 17.33. Now we have a gamma AB average as given here, and we have RW12 also given here. Now calculating the ultimate bearing capacity from this expression. Putting this value in the above expression, we have average 17.33 times depth of foundation, which is 1.5, times NQ, which is 42, times RW1, which is obtained as 0.83, plus 0.5 gamma set as given in the question. We have gamma set as 20, and change in the width is 1.5 times n gamma, which is 46 times 1 minus 0.2, and 1.5 is the depth of foundation, by 2.3 times 0.5, which is RW2 as obtained above. Now this gives us, calculating this gives us 10 times 50, 500 times 1 plus 0.2 and 3 by 2.3. Similarly, this gives us, let's calculate this using calculator, which provides us 309.46 plus 300. So we have you obtained as 17.4.68 kilonewton per meter square. Now we have net ultimate bearing capacity as Q minus in this time we are going to take the average unit weight and multiplied by depth of foundation, which gives us 74.68 minus 17.33 times 1.52, and calculating this using calculator, which gives us 1748.69 kilonewton per meter square. Similarly, we can calculate the same load, QS equal to QNS plus gamma AB, that is the average unit weight, QNU by F. This gives us 608.89. This is the factor of safety. This is how we can calculate the safe load needed for the putting as asked in the question. So this is much for the today. In the next video we will solve the more numerical from this chapter. And one message for the viewer is that we can comment the topic on if you want a video lecture, so that we can provide you the lecture what you are expecting from us. Till then, bye, all the way.